Hi, we are Team B6 SoundSync. Welcome to our project. SoundSync is an automatic digital page turner designed for musicians. Our motivation for SoundSync is the page flipping problem. When a musician is playing music, whether it be during practice or performance, failing to turn a page can result in a loss of focus and disrupt the musical balance. Current solutions include Bluetooth foot pedals and human page turners, both of which are susceptible to failure. Therefore, we propose a system that autonomously turns pages in real time using gaze tracking and audio processing to ensure accuracy and focused playing for the duration of practice. We begin with setup, where a user can upload their music, select their instrument, and calibrate their eyes. Once these steps are complete, with the microphone and eye tracking peripherals securely attached to the laptop, we begin back-end processing. Our backend system is divided into two subsystems, one for audio and one for eye tracking. The audio subsystem uses the short-time Fourier transform, chroma vector analysis, and dynamic time warping to precisely calculate where a user just played. The eye tracking subsystem uses a rules-based heuristic combined with override functions to determine when a page should be flipped. Together, the subsystem outputs are combined to send to the front end two important messages: the location of the cursor and the page number to display. Here, the front end displays the data in real time using jQuery. So now this is a video demo of the eye calibration steps. First, we adjust the camera position to align to the laptop screen. Next, I'm going to fast forward through this video of the user musician calibrating their eyes. Once the eyes have been successfully calibrated, you can visualize where a user's gaze is on the screen. So for our web page, we begin with a terms and conditions screen. Here, the user is told how their data and eye tracking information is stored and used. The next page is calibration for the Tobii Eye Tracker 5. There is specific software that needs to be installed in order to be able to use this eye tracker camera, which is what this external link is for. And finally, this is the page where users can upload the actual sheet music that they will be playing, as well as the corresponding MIDI or sound file that accompanies that, as well as selecting their instrument. And finally, we're onto the play page where their sheet music is displayed. You can notice that the cursor is stuck at the top left of the page for now, because no audio input has been played. And we also have 3 buttons at the bottom for users to either use the audio system only, the eye tracking system, or a combination of both. The front end uses a model view controller architecture to seamlessly integrate the backend components and the real-time data collection with the user interface. The backend uses Django and Python, while the front end is built from HTML and CSS with JavaScript and jQuery to handle the cursor movement and page flipping functionality. This is a demo of the functionality of the eye tracking subsystem.
For our eye tracking implementation, we use the Tobii Eye Tracker 5 camera. We chose to use this camera because it provides the best starting precision data and best latency that fits our previously mentioned design requirements, while also falling within our budget. For example, the initial startup of the eye tracking model has a latency of 250 milliseconds. but on average the camera has a latency of 30 milliseconds. The eye tracking data from this camera is fed into a heuristic model that was built in C++. This model outputs which row and bar the user is looking at, as well as whether or not to turn the page. This stream of outputs is sent to the back end of the web application. The reason why we send row and bar information is to further help the audio alignment model as a measure of confidence to avoid aligning to segments that are too far from where the user is currently playing. Lastly, the heuristic model we developed checks for different thresholds. These include whether or not the user is looking at the turn page forward button, whether or not the user is looking at the turn page backward button, and lastly, if the user is constantly looking at the last line for a duration of 2 measures. If these thresholds are met, then the model sends a 1 for a forward page flip, a 2 for a backwards page flip, and a 0 to not turn the page.
As mentioned in the beginning, audio alignment uses a technique called chroma vectoring to extract the notes played and align it to note sequences in the reference MIDI. This begins with taking a segment of recorded audio and taking the short time Fourier transform to retrieve the frequencies. These frequencies are then assigned to 12 bins, each associated with a note in the 12-tone Western major scale. The net result is a sequence of these chroma vectors that show what note was played for what duration of time. For instance, this dark bar here shows that the note A was detected for approximately 200 milliseconds. One note here is the grays right above and below this A are due to noise from the short time Fourier transform and are easily filtered out by setting a threshold that filters out any area that's not dark enough. Importantly, because this graphs a large NumPy array of chroma vectors, processing data in this matrix is fast and only comes out to about 20 milliseconds. Although the processing time is low, the time it takes to retrieve this data is relatively much longer. Because we extract the notes from a recorded segment of audio, if recording time is too short, we won't have enough notes to properly align it to the reference MIDI. However, if the recording time is too long, the frequency of audio alignment will be too slow, and the audio alignment won't react fast enough to the user. In the end, we changed the duration of recording to be a function of the average duration of a note. This means on faster pieces, we will record shorter durations because we will know we will hear more notes in a shorter amount of time. And on a slower piece, we will record for longer durations to get enough notes to align. In the case that this is messy, harmonic percussive separation is a technique added to help smooth out the data. As the name suggests, the function separates harmonic and percussive sounds and leaves us with just the harmonic content. Filtering percussive sounds causes the chroma vectors to be much cleaner, at the cost of nearly quadruple the processing time. Therefore, harmonic MIDI align is only called if the first MIDI align function is unable to get a clear sequence of notes. Lastly, we have dynamic time warping. As the most robust algorithm, it costs the most amount of time. The function operates by aligning physical points between two audio sequences using a cost matrix. The calculation of this cost matrix is time intensive, and its time complexity is a function of nearly both the time sequences. Therefore, for slower pieces where the audio recordings are longer, this algorithm can take nearly 500 milliseconds. Therefore, although this algorithm is extremely robust to wrong notes or changes in tempo, the latency associated with it means it's called very rarely, but serves as a valuable backup. Overall, this shows how audio alignment is used to gain the sequence of notes we will check for in the reference audio, and eye tracking serves as a supplement to give each of those sequences a confidence that allows us to ultimately choose the correct sequence of notes to align to. We then used the system to see how well it performed. We looked at the back-end latency and how well it flipped. We looked at how well eye tracking improved audio alignment. We looked at how accurate and robust audio alignment was, as well as how robust eye tracking was. Ultimately, we were proud to have built a system that solves a crucial problem for musicians around the world.